Hi, my name is Andrew Walsh, and I'm a master's student at Oklahoma State University, and today I will be presenting over the design, development, and flight testing of a micro-air vehicle for meteorological data collection. The motivation behind this research is to increase atmospheric boundary layer, or ABL, monitoring and data collection, which in turn improves weather predictions. In Oklahoma, this is particularly important because improved weather predictions means improved ability to predict tornadoes, which saves lives. It also reduces the economic impact of this severe weather by providing better forecasting to companies so they can plan their logistics around the impact of the severe weather. The problem is ABL monitoring isn't easy. It's very dependent upon time and location, so you need to cast a wide range of sensors to accurately know what's happening in the ABL over a large area. Currently, there are a couple different methods used for collecting ABL data. The first is mesonet towers, which are roughly 30 feet tall towers scattered throughout Oklahoma, and they do a good job of providing ground level readings, but they don't really provide a capability of taking atmospheric measurements further up at higher elevations in the atmosphere. The next is weather balloons, which are essentially these giant balloons released with sensors on board, and as they rise up through the atmosphere, they beam the data back down to the ground so scientists can use it to evaluate forecasts. And in recent times, unmanned systems have begun to be used, and these are really good if you have particular areas of interest. You can fly them in and you can take multiple readings at multiple different elevations and just get tons of data. So just to give a little bit more background on weather balloons, they do have their downsides. You can't control how fast they ascend or where they drift to, so that limits the amount of data you can collect, obviously, and there's also the issue of cost. Each year, 75,000 weather balloons are launched in total per year from 92 different sites across the United States. Of those 75,000 balloons launched, only about 20% are able to have their radiosonde payload recovered. With each radiosonde costing approximately $200, that comes out to around $10 million lost in radiosondes per year. Not to mention the fact that these radiosondes have metals and batteries in them, and so when they're just left in the environment, they end up polluting it. This is where I'm proposing a system that combines unmanned aerial systems with weather balloons, where instead of launching just a radiosonde, you're launching a micro-air vehicle instead that's outfitted with the same sensors, and the balloon carries it up, and then at a specified altitude, you drop one or multiple of these vehicles, and they spread out over an area and circle down, collecting data as they get closer to the Earth's surface again. And then once they reach a specified altitude, they're able to fly back to one central point where they can be collected, refurbished, and reused. And a mission like this really isn't a novel idea. There are a few different groups that have attempted a similar mission before, and I've highlighted those vehicles on this slide. But when it comes down to it, they all either suffered from being too difficult to control or recover, or being too heavy to be realistically deployed in the real world. What I really wanted to do when I was developing my system was look at these previous designs and take note of what they did well, but also look at different ways to improve them. And the three main areas I identified are making the vehicle lighter weight, specifically in the US under 0.55 pounds, so there's less regulatory hurdles from the FAA to jump over. Make the vehicle cost less and be less complex, so it's simple and easy to manufacture and cheap to replace if it breaks, and also ensure robustness of operation by putting a motor on board so it can handle gusts of wind. With these points of consideration in mind, I have developed the Sparrow aircraft. And in order to keep the cost and complexity down as much as possible, for the airframe of the aircraft, I've used as many off-the-shelf components as possible. Really, everything on it could be purchased off of Amazon or from a hobby store, with the exception of the 3D printed enclosures on the forward and aft section. And if this vehicle was ever scaled up to mass production, these could easily be produced using a technique such as vacuum forming. Here are the performance characteristics of the Sparrow vehicle. The lift-to-drag ratio and cruise velocity are fairly comparable to other micro-air vehicles of this size. The endurance is roughly 30 minutes at 50% throttle, and the sink rate is 6 feet per second, which is slower than the ascent rate of a weather balloon, allowing for more data to be collected in a vertical column, which is beneficial for monitoring the atmospheric boundary layer. Here is the avionics setup for the Sparrow vehicle, and once again, these are just all off-the-shelf components. There's nothing custom manufactured or custom made. For testing, I have a receiver that allows the vehicles to be controlled from the ground. However, in a fully autonomous implementation, the receiver could be removed, allowing for slightly more weight and payload volume if in the future any additional sensors needed to be added onto the vehicle. So obviously the whole point of the Sparrow vehicle is to collect atmospheric data. And to do so, initially the plan was to implement pressure, temperature, and humidity sensors on board. However, due to a global shortage of pressure sensors, I was only able to implement the IST humidity and temperature sensor and the IMET temperature sensor on board. And in order to store this data, I am using a Teensy 3.6 running custom logging software developed by Oklahoma State's Unmanned Systems Research Institute. And this data acquisition unit allows us to log data at 200 hertz. And there is currently work being done on allowing this data to be sent back down to the ground as it is gathered, which would provide valuable information to scientists in real time. So collecting data is one thing, but it's also important to make sure that the data being collected is actually correct. And to do this, OSU has already completed flights with these sensors in conjunction with OU, and the data between those two flights have been compared and shown to be accurate. And so for the Sparrow vehicle, I'm going to integrate the sensors in a similar fashion to how the sensors were integrated into those previous flights, which shows that they should collect reliably. However, to make sure, I'm also doing a comparison with an IMET sensor, where I will fly an aircraft with just my fuselage attached under one wing of a bigger unmanned system, and the IMET sensor attached under the other wing, and data between those two sensors will be compared post-flight to see the accuracy. In conclusion, there are some significant advantages to pairing the Sparrow vehicle with a weather balloon. You get higher resolution vertical data than with just a weather balloon alone, with the sink rate of the Sparrow being less than the ascent rate of the weather balloon. The Sparrow is also cost effective, with the fuselage costing less than $15, and the avionics do come out to around $500, but that price could come down through either bulk ordering or designing a more custom board that's specified for this purpose. The Sparrow weighs less than 0.55 pounds, which reduces FAA restrictions on its use, and it is a robust system with a propeller that allows it to overcome wind gusts. For future work, there are plans to turn the front of the vehicle into a multi-hole probe for more accurate wind direction and velocity measurements. Also, there are plans to make the wings folding for deployment from a rocket. Thanks for your time.